Good day, everyone. I'm Roy Richardson, Vice President of Business Development for CelPlan Technologies. Welcome to the CelPlan webinar on MIMO, What is Real, What is Wishful Thinking. The presenter today is Mr. Leonard Kurowajczyk, who will give a more detailed introduction of himself once I turn the floor over to him. Before that, just a few logistics to go over so that you can browse through the session. During the webinar, you will note that all attendees will be in listen-only mode. We will take breaks during the presentation to answer questions, so please type in your questions. You will see in your panel that there's a hand icon that you can actually raise to ask a question. Please note that due to time constraints, we may not be able to get all of the questions during the session. However, those that we're not able to get to, we will at least answer via email. Depending on your internet connection, you may encounter screen refresh issues from time to time. If that does occur, please click on the button that toggles from full screen to window and back to force an update of the screen. Also, there's a chat window where you can ping us if you encounter any issues during the webinar. And with that out of the way and without further ado, I will now turn the session over to Leonard. Leonard?
Thank you, Roy. Good morning, good afternoon, good evening. We have the audience from all over the world, and that's very nice. Let's start the webinar. MIMO, what is real, what is visual thinking? I would like to introduce myself. If you were not part of the other webinars, I am the CEO and CTO of CelPlan International. More than 45 years experience in the telecom field, always in R&D, manufacturing, and service areas. I have several patents, and we as a team have published several books, designing CDMA 2000 and LTE WiMAX and WLAN network design. We are writing now the second edition of the LTE WiMAX and WLAN network design. It should come out beginning of next year. Our target was December. It probably will slip a little bit. And we are also working on the network video, backhaul network design, multi-technology networks, and smart grid network design. So those are the books that we are writing and collecting materials and so on. And you can see the covers already that are prepared by Wiley. A little bit about our company, CelPlan International. We are an employee-owned enterprise with international presence. We are headquarters in Reston, Virginia in the USA. We have about 600 employees already. 20 plus years in business, subsidiaries in 6 countries with worldwide operation, totally vendor independent, and we do network design software, network design services, we optimize network, evaluate performance of networks and so on, and we provide services to vendors, operators, and consultants. We do all kind of high-level consulting. Generally, when people have a tough issue, they come to us to look into it, and we like, challenges. We do managed services, and we support all technologies, multi-technologies, multi-band, and so on, including, backhaul, small cells, indoor, head nets, and Wi-Fi offloading. This is a webinar from a series of webinars. We already gave 6 webinars, and now this is the 7th webinar, the last webinar for this year, and we are very pleased to do it, to perform it. We have great audiences. The webinar number 1 that was about dimensioning of user traffic. All those webinars are accessible in our website and also on YouTube. This already passed 1,000 views in YouTube. And basically we characterize user traffic, and it's very interesting. It's one of our most popular webinars in this series. Webinar 2, how to consider overhead in LTE dimensioning and what is the impact. 545 views. The live webinar had people from 49 countries. And here is the summary of the contents of the webinar. The next webinar was in July, how to consider customer experience when designing a wireless network. 467 YouTube views until now, and here are the topics that were discussed in the webinar. The next webinar was in August, LTE Measurements, what they mean and how they are used. 686 YouTube views, 44 countries, also very successful webinar, and was very extensive, a lot of information from network measurements to field measurements. Webinar 5 was what LTE parameters need to be to dimensions and optimize. This webinar was divided in two. The part 1 covered the downlink. We had participants for 69 countries, different countries, and the YouTube views already passed 1,200. So it's very, very, very popular webinar. The uplink part had a little bit less interest. We had only 316 views until now, although, you know, the webinar was later and still picking. The last webinar was spectral analysis for LTE systems, was in October. We have, he is X, but we have participants from 45 countries, I believe, and 145 YouTube views. And here is the contents of the webinar, Very detailed webinar also. I would like to call attention, we have an LTE technology network design and optimization bootcamp. This is a live bootcamp. We did it last year with great success, great feedback from the participants. It will be from December 8 to 12. It's a whole week, 8 hours per day at the University of West Indies in South Augustine in Trinidad. Really recommend that you participate. So if you like our webinars, you will love this class because we have opportunity to go much deeper and we have much more interaction with the audience. And these are the topics of the webinar, the contents. We have several modules. And there is a optional certification. So with this introduction, let's go to today's feature presentation. And this is webinar number 7, MIMO, what is real and what is wishful thinking. The content of this webinar is the following. We will give a little bit of support theory. And I find this very important in this webinar. We didn't do this in the other webinars. But MIMO is very complex and it requires the understanding of certain mathematical concepts and also of some signal processing concepts and so on. Unfortunately, we don't have much time to go very deep, so I selected the most important topics. Some of the topics are very unique to the way the CelPlan sees things, and I really suggest that you pay attention because this will be very, very important for the remaining of this webinar. Then we have the antenna ports. We will speak about antenna ports, transmission modes, and RF channel. So all of this basically is a kind of support for the webinar, today's webinar, that is MIMO. In MIMO, we will speak about the different MIMO solutions, and in each solution we will address and we will discuss specific topics that they may be presented in the first solution, but many of them, they're applicable to the remaining solutions and so on. So we try to give this more or less in hierarchical order, and we introduce during each one of those MIMO configurations, we introduce basic concepts and basic solutions and so on. Then we will speak about antenna correlation, advanced antenna system, a little bit about MIMO performance, and just a glance on our new products. So let's speak about support theory. Support theory, we'll speak about mathematics and signal processing. In mathematics, I would like to cover polynomial decomposition, exponential numbers, and matrices. In our class in UWE, you will see that we go much more in depth and we have much more time. Basically, the mathematics is a whole half day, so about 4 hours. Basically, in terms of polynomial decomposition, Taylor, what he found was that it was possible to decompose a polynomial, a function, through a sum of its derivatives. And this was a very, very important conclusion. And if we bring this to the zero crossing, we will have the Maclaurin series, and this series then it's a little bit easier to implement and to do the calculations. But why are we interested in this? Because there are two functions that are essential for anything we do in RF, including MIMO, that are the sine and the cosine. But the sine and the cosine by themselves, there isn't a function that does it. We have it in our calculator, but the calculator doesn't do magic. So the calculator really, to calculate the sine and the cosine, or it uses a table, or it does a polynomial decomposition. So that's what is very, very important. And as you see here in the polynomial decomposition, the only thing we need to know is the derivatives. The derivative of the sine is the cosine, and the derivative of the cosine is the minus sine. So they are recursive. So the second derivative, the third derivative, and so on, they keep repeating themselves. So this is very, very good. And because sine of 0 is 0, and cosine of 0 is 1, and we are doing the Maclaurin series, we can calculate the cosine of 0 and the sine of 0, of theta, sorry, not 0, of the cosine of theta and sine of theta. And this gives us this function here that then depends only on the angle, theta. So it's possible to calculate the value for any angle. Angle here is expressed in radians, of course, so we can then calculate sine and cosine for any angle. So really, Taylor's breakthrough was fantastic. You know, it's something amazing, and this was done in 1712. Well, another expression, another function that we use a lot is includes an exponential number. And I see that generally engineers, they try to, shut off and, well, that's exponential, I don't understand it. But it's much easier than it looks. Basically, this is explained in great details in our regular class. Everything started from this function, a to the power of x. And basically, using the Taylor expansion, we can calculate a to the power of x. And when the limit goes to 0, we see that this function will be, the a will be between 1 and 2. So we know that it's greater than 1 and smaller than 3. So we start moving and finding what is the value that will give me a derivative the same as the function itself. So, and we find that the derivative starts repeating when we use a equal to 2.718, and this number was then called the exponential number. So the derivative of e to the power of x is e to the power of x, and that makes us easy to do the Maclaurin expansion. So if we do the Maclaurin expansion for e to the power of I theta, that's what we get. Well, so we can calculate now e to the power of I theta, but if we look at this, we will see that the real part is this and the imaginary part is this. And if we go back and compare this with the sine and cosine, oh, e to the power of I theta is equal to cosine of theta I sine of theta. So basically what we have here is that the exponential function here is really a sum of a cosine and a sine. And this is used in the modulation, and this is used also in OFDM and everywhere else. So you may see mathematical expressions using cosine and sine, or for economy of space you can use, you can see an exponential number. So don't be scared, and it's basically just a notation. And this exponential number, as we rotate theta, it rotates in a circle, the same way like the sine and the cosine. For MIMO, we need to understand matrices, and I cannot give you everything, a refresher about matrices here in this webinar. I will just call some very important things, basic, that you will need to understand some of the things that we'll discuss in MIMO. Well, first is that the matrix is a rectangular array of numbers arranged in rows and columns. So this is a row and this is a column. And this is the notation, so A11, A12. So the first number is a row, the second number represents the column. And this is standardized, so everybody speaks the same language, mathematics. And we can then express a series of numbers by a matrix. So here we have a series of equations, and then we can express these equations in matrix. Oops, is this something wrong? No, it's not wrong, because in reality we have three variables. So I should put another variable here, but this variable is 0, the coefficient. So, but in the matrix I have to represent all the variables and the results. So the above matrix, this matrix is 3 by 4. We say 3 by 4. Okay, it's 3 rows by 4 columns. Okay, we have several types of matrices. We have a regular matrix that is square, or a regular matrix that is rectangular. But there are some specialized matrices. So we have an upper triangular matrix where on the bottom all the numbers are 0. We have a lower triangular matrix. On the top all the numbers are 0. We have a diagonal matrix that everything is 0 but the diagonal. And we have the identity matrix where everything, the diagonal is 1. So, and the reason that I'm telling you this is because if you read about MIMO, people will throw on you those names. And it's important to understand what is an identity matrix, okay, what is a diagonal matrix, and so on, and also be able to understand, you know, references to rows and columns and matrix size and so on and so on. Well, you also will need to know a little bit about addition of matrices, and addition of matrices is very, very simple. You just take the same terms and you add them. You see? Very, very simple. Same thing to the subtraction of matrices. Very simple also. But in both cases, the matrices must have the same size. Another easy operation is the scalar product. So 2 times a matrix, you just multiply everything by 2. So those are the easy operations. Now let's go to the more complex operation. One of the complex, not complex, but something that you need to be very careful when you plan to do it. But even if you don't plan to do it, you need to understand what it means. So that's why I'm presenting here. So here we are multiplying a matrix A, but a matrix B. Well, you will say, oops, but you said that they should be the same size. Not for the multiplication. For the multiplication, A must have the same number of columns as B has of number of rows. So A has 2 columns, B has 2 rows. So 2 equal to 2. Okay. And so this 2 by 3 times 3 by 2, it will give a 2 by 2. A 3 by 2 times 2 by 3, it will give us a 3 by 3. And a 2 by 4 times a 3 by 2 just does not exist, because this number is not equal to this number. Okay, so let's go then to the product, and the way that we do the product. So this is 3 by 2 times 2 by 3 is a 3 by 3 matrix. And then here we have what we do. We take 2 times 0 minus 1 times minus 2. 0 times 0, 3 times minus 2, 1 times 0, 0 times minus 2. And that's what we have here. And we proceed with the other columns and so on. And then we get the product matrix. Okay, you don't need to memorize this. There are softwares that do this for you if you need to do. But you need to understand what is involved. Another thing that we need to know is matrix operations. So there are several operations that we can do on a matrix that really don't change the matrix. So one of them is row switching. So we can change where the row is in the matrix, and nothing happens to the matrix, because basically what we are doing here, if these are linear equations, we are just changing the position of them, the order, so it does not affect. We can also multiply the rows by certain numbers, half, minus, plus, and nothing changes. It's the same as if we are multiplying those equations by some numbers. And then you will see, well, why do you want to do this? Well, all of this is done to allow us to eliminate variables in certain equations. But to do this, we also must be able to do row addition. So what we can do here is that we can add certain rows and create replace one row by, suppose I am replacing here 2 times row 1 plus row 2 by this row here, and I still have the same matrix, so there is no difference. So those operations, they are really being used to simplify the matrix and to allow us to extract some of the variables. There is a concept of echelon of a matrix, and this concept basically leads us toward eliminating in a matrix some redundancies, because I can have 3 unknowns with 3 equations, but one equation supposedly is the double of the other. So they are not really independent equations, and I cannot solve with those 3 equations my problem. And basically what the echelon allows us is a technique that allows us to find out how many independent equations do we have. And this is what defines the matrix rank. So it's very, very important to know what is the rank of a matrix to see, if we can solve the linear equations or not. And so basically that's very, very important. And it relies on the a row echelon of the matrix. Another concept is the matrix determinant. The matrix determinant really assigns to each matrix a single number. So a matrix A has one determinant. So a determinant of a 2 by 2 matrix is very simple. That's it. Just be careful, this is not a minus. This is a, just to show that it's a new line. And for a 3 by 3 matrix, it's a little bit more complex. So what is done here, it is we use the rule of Saros. And what we do, this is the original matrix. We repeat the first two columns, and then we go like this. I apologize that the arrows are a little bit misplaced. And we do the products. Or we can use then the Leibniz formula, that is a very complex formula. And the calculation of the determinant really grows exponentially with the size of the square matrix. So after 3 or 4, you need really a computer to do it. Well, so we spoke about subtraction, addition, product, but we didn't speak about division. Well, there isn't a concept of a division of a matrix, but there is a concept of an inverse of a matrix. And so if we do then a product, we sort of are doing a division. And the inverse of a matrix uses a property that a matrix times its inverted matrix is equal to the inverted matrix times the matrix, and it's equal to the identity matrix. So you remember we spoke about the identity matrix or ones on the diagonal. So that's how we will use this expression to allow us to do the matrix inversion. And this is exemplified here. So we start with this matrix. This matrix is then put here. And here we have an identity matrix of the same size. Well, what we will do now is we will apply row operations. Multiply rows, add rows, and so on, until we can shift the identity matrix to the other side. So what is left on this side will be the inverse matrix. Now I would like to tell you a little bit about matrix theorems. I will not go one by one here. You can browse later on. You can keep this as a reference. But rules that are very understandable for that we have in our heads for numbers, they are not always applied to matrices. And that's very, very important to understand. So there are some rules that are different. Suppose A times B is not B times A. And there are many other matrix operations, and of course we don't have time to discuss all of them. You can browse by yourself. Sum vector, mean vector, deviation score, sum of square, cross product, variance, covariance, norm, and singular value. Some of those we will discuss later on when we are talking about MIMO. Well, mathematics is done, so we go to the next step, that is signal processing fundamentals. In signal processing fundamentals, we will discuss digitizing analog signals, orthogonal signals, combining sine waves, and carrier modulation. Well, probably all of you are familiar with the Nyquist sampling theorem. When you need to the frequency should be twice the bandwidth and the number of samples 1 over the sampling frequency, the sampling period. So basically then any analog function can be represented by a set of numbers, and that's what allows us to use, you know, all those digital technologies like OFDM and so on. People are very used to sample at the baseband, but you can sample anywhere. You don't need to sample at the baseband, and this is the formula that allows you to calculate what is the sampling on frequencies that are not on the baseband, but they are shifted in frequency. Another aspect important is that how do we represent a signal in the frequency domain? Basically, what we are transmitting today is bits. Bits are not return to zero elements because they have 1 and a 0. So a bit is either a 0 or a 1. Well, when we map bits to symbols, we want the symbols to be that they don't have a depolarization. So we make them +1 and -1. So a 1 bit gives a +1 and a 0 bit gives a -1, or vice versa. It really doesn't matter. Well, what is the spectrum of something like this? Well, the spectrum of this is what we call the sinc function, or sinus cardinalis function. And this function is defined by this formula. And this is my pulse bandwidth. So basically there is a relationship between the bandwidth, the time, the duration of the symbol, and the sinc function periodicity. See, this sinc function, it crosses 0 every period. So here it's for a half a second, here it's for 1 second duration pulse. You can see how larger the pulse, closer is the frequency spectrum. Another very important, well, I forgot to say, is this sinc function that then allows us to stack subcarriers side by side without one interfering to the next, and that's what allows us to have the OFDM technology. Well, let's speak about orthogonal signals. What means orthogonality? It means that if you have two signals that are orthogonal, they can be detected independently of each other. It means that it doesn't matter the strength of one signal, I can detect the other and there is no interference. But we are speaking here of digital signals. So how do we know if a digital signal is orthogonal or not? Well, we take the samples over an entire period of both, and we do what is called a dot product. So we multiply the samples. Of course, they need to be synchronized. We multiply the samples and we add the results. If the result is null, it means that the two signals are orthogonal. And this is the main property also used in OFDM. And what are the signals that are orthogonal? Well, a sine and a cosine, they are orthogonal signals. And that's very, very important. So, and that's what we use. Suppose we define an I and a Q, we are defining orthogonal signals. So that's why we can send information on I and on Q. And one is in phase, the other is in quadrature, 90 degrees, but the sine and cosine are exactly this. Sine, if you consider sine as a reference, the cosine is 90 degrees, is a sine 90, shifted by 90 degrees. And because sine of x times cosine of x is 1/2 of sine of 2x, well, if we do the integral, we will see that this is 0. And this principle also is used in OFDM, but OFDM uses another functions that property of other functions that are orthogonal to themselves. And here basically what we say is that harmonically related signals are orthogonal. What is harmonic signals? It's the ones that have multiple frequencies. So frequency of 1, frequency of 2, frequency of 3, frequency of 4, they are all orthogonal to each other. And that's what allows us to stack 1,000 subcarriers one beside the other, because they are multiple of the spacing between them. And that is the fact because the integral of sine x times sine of nx equals to 0. And here we illustrate 1, 2, 3, 4. A 4 frequency or 4 subcarriers composite signal. That is this signal here in light blue. And we implemented this here in Excel. And you can see that we are able then to detect also if one of the frequencies is missing or has a different value. This principle here, it looks so obvious, but it is so important that I don't think I ever stress it enough, because this is what you need to understand to interpret the behavior of the RF channel. So basically, if you generate a sine wave and you send it through the RF channel, what will happen in the reception is that you will get not one sine wave, but multiple sine waves that are caused by reflection and so on, and each one will arrive at a different phase, like we are illustrating here. But here we are assuming that everybody arrives with the same amplitude. So what happens now is that we have here several sine waves. If we add them together, we get this red, dark red waveform. That is, and that's very, very, very important. It's also a sine wave, and it's also of the same frequency. So there is no change in frequency due to multipath, and there is no distortion to the multipath. There is only a change in amplitude and phase. So that's something extremely important to understand, that the combination of several paths results in a single waveform that is the sum of all those paths. And basically what it does, it changes the phase, it assumes the phase of the components, it's a weighted phase of the phase shifts of each component, and also a weighted of the amplitude. And finally, one of the last concept is carrier modulation. Basically here we have the I-axis and the Q-axis, and this is a way of represent a constellation. But basically what happens is that, suppose this is BPSK, and I forgot to put the name here, SK, Okay. So what happens here is that we have a sine being generated with this amplitude and another sine 180 degrees out of phase. And those are my two states. So either I send one or I send the other. And each one of the states carries one bit of information. Then we go to QPSK. And in QPSK, basically, we have now 4 states. And each state will have a sine and a cosine. And those are transmitted at the same time. Okay, and basically this is one of the symbols, this is another symbol, and each symbol carries 2 bits. Then we have 16 QAM that the symbol carries 4 bits. So this symbol will have a sine of this amplitude and a cosine of this amplitude. So it can uniquely be decoded. And 54, finally we have the 64 QAM. Okay. And here we illustrate, what happens when we transition symbols. Of course, there are much more sine waves in the middle here. We compressed it, but basically there is a phase change each time we transition symbols. And if we go to a larger modulations, then amplitude also plays a role, and you can have things like this. And this basically here we show the carrier modulator. We have the I data coming here, the Q data coming here, and basically this data will modulate then a carrier shifted by in phase or contra phase, shifted there by the carrier frequency. Well, next we will speak a little bit about the RF channel. And RF channel is something very, very complex because it's not just one, waveform that arrives in a certain point. So here we illustrate that there is a transmitter, and this transmitter, although it's sending only one waveform, this waveform will hit obstacles and it will arrive at the receiver through many paths. And that makes the detection of the RF channel very hard. Up to today, we tried to predict, what would be the multipath effect in the different areas of the network. And for this, we developed the K-factor prediction. This K-factor gives us an idea of how the RF channel is affected by multipath depending on certain constraints on certain parameters. So basically here we have, you see the different multipath components arriving at different times within the same symbol. And here we have the K-factor for different values of K-factor. So basically what we do today to help to understand multipath, because multipath can be very disruptive, is that we calculate, we predict the K-factor along a whole network. And we use those parameters here. This formula is used here with these formulas here that we are using now to calculate per pixel basis what is the expected signal distribution and how much it was affected by multipath. So a multipath that has a high value, more than 10, it will indicate that most probably the signal follows a Gaussian distribution, and most probably it doesn't have much multipath. But if it is below 2, well, it's a low coherence signal, and the multipath signal follows a Rayleigh distribution. And so it's subject to a lot of fadings and so on. So the SNR required for a high K factor and the SNR required for a low K factor, they are totally different. You need much more SNR when you have a low K factor. But this was okay, you know, until 2G, 3G it was already problematic because the channels became much larger. CDMA was 1.2 megahertz, okay. UMTS already 5 megahertz, so the channel now doesn't have a uniform behavior. And we had difficulties in predicting or in even guessing what will be the channel behavior in the different networks, in different arrangements and so on. And there was nothing available in the market that would allow us to do those measurements in a practical way without being a $100,000+ test equipment to be used in the lab. So we decided to develop an equipment ourselves called CelSpectrum, and this equipment is based on a universal soft-defined receiver. It captures spectrum and analyzes spectrum from 100 megahertz to 20 gigahertz range, because this was another problem. There are so many bands, you know, popping up that was very hard or nearly impossible to have equipments for all those bands. So we tried to do something that is highly flexible, and we analyze up to 100 megahertz bandwidth at a time. And this equipment is a spectrum analyzer and a technology analyzer at the same time. We can decode, we plan to decode multiple technologies. Today we are doing only LTE, and it is ideal because of the size and weight and power consumption for drive and walk tests. But one of the main differentiators of CelSpectrum is that it not just does the measurements, it captures and stores the entire spectrum in the bandwidth being measured. So this allows us to analyze the spectrum, you know, much later, to go and drill a little bit more and so on. So by capturing the whole spectrum, that's really a very unique feature, and you will need to buy 2, 3 different equipments to do something similar at, you know, lab prices. And the CelSpectrum basically is used for what? Well, it provides very important insights into multipath, fading, and antenna correlation. Okay, CelSpectrum. This was really, I will just give a very, very brief introduction here. I don't want to be promoting, but mainly to understand what it does. And it does the LTE channel response per resource element. It does multipath delay spread analysis, frequency fading, time fading, noise floor, interference, traffic distribution, and has an unbelievable 3D visualization capability. This is a screenshot of the spectrum analyzer here, and this has any regular spectrum analyzer, but much more precise and much more flexible. and also we store basically the spectrum analysis, and this can be replayed at any time. And CelSpectrum spectrum analyzer we can use also during a drive test. That is not very easy to do with a regular spectrum analyzer, because we can connect a GPS and we can collect the spectrum as we drive by. So, and that lowers a lot the costs of the procedure, because we can hire a taxi driver. The taxi driver just drives according to a certain route, and then later when he arrives, the engineers can analyze the spectrum today, tomorrow, next week, whenever it's convenient. And then let's speak a little bit about RF channel technology analyzer, and we will exemplify a mobile channel characterization and a stationary channel characterization. Well, so what we are showing here is that this is a bird's eye of 6 frames. Here are the frequencies and here are the symbols. Because we didn't zoom in, we have the same thing here. So this is a bird's eye or of what we are watching here in 3D. In this case is a line of, this is the received line of sight signal. And what we did, we sliced this in frequency, in time, excuse me, here. And this was sliced on symbol 0. And then in the middle, we sliced in frequency that this was about subcarrier 300. And you can see here that there are big variations and so on the received signals, because of course some of the signals are off, some of the resource elements are not transmitting any, we're just measuring noise and so on, but some are, but the signal is not equalized. Now what happens when we go to a non-line of sight signal? Well, things are even worse, because the changes are larger and so on. So you can see here that, you know, the peaks, very large peaks of nearly 40 dBs and so on distance. So what we did, we looked at the channel response. And for the channel response for line of sight signals, you can see that the channel is more or less flat. Here we show the changes with time, but this is very few dBs. I think this goes from 49 to 53 dBs. So it's about 4 dB change, that's it. And this is in frequency. Okay, so here we have frequencies. So you can see that the channel is relatively well behaved, but when we go to, and we can compensate those variations. But you can see that the non-line of sight signal, it's much more variable. So it's much harder to compensate, mainly in terms of time and frequency. Time is a little bit, depends on the speed of the user also. Now let's see what is the difference, and all of those measurements that were done driving in a car at about, would say 40 miles per hour, 60 kilometers per hour. Now let's look what happens if we have a stationary device. So we are now measuring a non-line of sight indoor, and we are doing the same measurement, but now with the measuring device stationary. And basically what we see then, well, we still have variations, but the variations don't change very much over time. And when we try to characterize the RF signal, the RF channel response, look what happens. It changes very, very little over time. And that's very, very important. You can see it's nearly flat. It has a fading here in one of the frequencies, but it doesn't change much. And those observations are very, 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 very important. And you will see why when we go into MIMO and we have to define, how much we can use MIMO, which kind of MIMO we can use, and if the feedback that we get from the mobile unit, if it will be good enough to be considered and to benefit from the knowledge of the channel. Because if the channel changes faster than the UE can provide a feedback, the feedback is useless. Okay, I think we still need 2 items. So we need to discuss now about antenna ports. We will speak about physical antennas, antenna ports, MIMO, and transmission modes. Well, there is a big evolution on physical antennas, and this evolution will change even more in the next years. We start using now multiple antennas to transmit signals. But to install multiple antennas in a tower and to assure that they will respect mutual distances and so on, it's nearly impossible. So what the antenna vendors are doing, they are creating antenna housings that hold multiple antennas. And here we are mapping different scenarios with a single antenna, a dual antenna in the same housing, a quad antenna, a cross-polarized antenna, a dual cross-polarized antenna, dual cross-polarized in the same housing, so that's 4 antennas. This is also 4 antennas. And then we have also a 8 antenna configuration. And all of them basically, because they are inside housings, with those 2 exceptions, B and F, that this distance has to be very well calculated and during installation. Otherwise, you have already the antennas configured and they don't move. Another concept that is very important is antenna ports. The concept of antenna port is to where the signal should be sent. And an antenna port can be connected to 1 antenna, physical, 2 or 4 or even 8. Or it can be spread between those antennas and so on. So basically defining the antenna port becomes very, very important to define how this signal is connected to each antenna. In the 3GPP downlink, we have 22 antenna ports defined. So antenna ports 0 to 3 are the most important one because those antenna ports, they carry the cell reference signal. The cell reference signal is a pilot that allows us to adjust, to calculate the RF channel response. On the other side, we have antenna port 4 that is used for broadcasting, MBS-FN. We have antenna 5, port 5, that is really used for beamforming without MIMO. So it's a single user beamforming. Antenna port number 6 is used for position location, location-based services. Antenna ports 7 to 8, they are used for beamforming with MIMO and multi-user MIMO, and the same for 9 to 14 and 15 to 22. And when we say that it's a certain number of ports, is that those ports, they can be connected to one antenna, physical antenna, 2, 4, 8, or 3, doesn't really matter. Well, it does matter, but the way it is connected and the way the signal is sent to a port, it's specified in the 3GPP specifications, and this defines, you know, how the signal will travel to the destination. Here we have the uplink antenna ports. Until very recently, we only had up to 2 antenna ports, but now we have up to 4 antenna ports per mobile terminal, per UE. Well, one way that people find that they could consider that there may be some increase in throughput would be to use the fact that we can deploy multiple antennas, and with this we get spatial diversity, and by spatial diversity try to increase the channel capacity. In the beginning it was basically to mitigate multipath, but with time it became also to send different informations through each antenna. And we need to understand that MIMO is a very general name, and it covers many different configurations. It covers single antenna transmissions. It covers transmission diversity in the transmitter and in the receiver, and it also covers spatial multiplexing, where different data are sent in different antennas. And this spatial multiplexing can be open loop, closed loop, and or multi-user. So, and we will drill into this in great detail as we go along. So the first release, release 8, it considered 2 by 2, 2 antennas of transmit to receive, up to 2 transmit, up to 2 receive, up to 4 transmit, up to 4 receive, and then the release 10, it considers up to 8 and 8. But you will see that the configurations are different. So it's not that we really have 8 antennas separate. They are treated really as a complex set of antennas that generate complex patterns. And in the uplink, the release 8 was only 1 antenna. So in the uplink we had 1 by 1. And then in release 10 we have 2 by 2 and 4 by 4. What are transmission modes? Well, we have so many antennas with ports specified, so we have different configurations. Transmission modes is something that is negotiated between the ENB and the UE. And this can be negotiated, this is negotiated when the UE enters the network and is renegotiated periodically. And basically, because the ENB and the UE, they exchange different kind of information, the transmission mode must support, in reality, more than one arrangement of antennas. And so we have today defined in 3GPP 10 transmission modes. We have the single antenna or fixed array, and then we have the MIMO. I consider the single antenna also a kind of MIMO, but where the M is 1, multiple of 1 and 1. Basically, MIMO defines how many streams enter the RF channel and how many streams leave the RF channel. So they are defined in relation to the RF channel. So MIMO in is how many streams are entering the RF channel, and MIMO out is how many streams are leaving the RF channel. And here in the bottom we have then listed what kind of physical antenna arrangements that we discussed previously will apply to each one of those transmission modes and so on. I will not go much more in details here because this can be very, very extensive, but it's something that is specified in the beginning and negotiated between the ENB and the UE. Here we have the downlink transmission modes, and we have up to 10 different downlink transmission modes, and here I give a lot of different information about it that again I don't have really time to explore, but basically each transmission mode, and we will see this here, this is the same information but it basically explains just in some more different details. Each transmission mode, it has in reality more than one arrangement. And the reason for this is that because it has a basic configuration and an advanced configuration. The basic configuration is used for common channels like broadcasting and so on, but it can also be used for UE-specific connections that cannot support the advanced configuration. So that's why every single transmission mode has two configurations, okay? And these are the uplink configurations. Okay, so finally we are ready to go into MIMO, but before we go into MIMO, let's have a break and I can have a cup of water and we can see if there are any questions.
Yeah, so Leonard, we have a few questions that have come in during your presentation. Number one, how does the receiver find the phase of the transmitted signal?
How the receiver finds the phase of the transmitted signal? Well, it's a very good question, and if you saw our previous webinars, you will see that the 3GPP provides a sequence that is a Zadov-Shu sequence. And this Zadov-Shu sequence is orthogonal to its own shifts. So this allows the receiver to analyze, to find out exactly where the Zadov-Shu sequence peaks. And with this peak, it really allows to detect, to synchronize with the phase of the transmitter. And then this Zadov sequence is also changed in frequency to one side to the other in such a way that the receiver is frequency synchronized and phase synchronized to the transmitter.
Okay, from the same person, how does multipath affect this detection?
Well, multipath makes it much more difficult because now you have several occurrences that are spaced in time. And that's why the sequence that was chosen by 3GPP is orthogonal to its own shifts. So by scanning in time, it's possible to find the main component and all of its multipaths. And that's what CelSpectrum uses to calculate what is the actual multipath at every single location. And also it's not possible to say what is the path and what is a multipath. The only thing we get is a set of multipaths. The strongest multipath is considered then as being the path.
Okay, we have a number of questions, but I'm going to probably take about three more. CelSpectrum detection of the mobile spectrum shows that the channel varies every few symbols. How does the LTE channel realimtation work in this case?
Well, you probably are probably working, whoever asked the question is working with MIMO already, and that's a critical issue in LTE or in any technology really, is that if the channel is not stable, there is a certain delay between the moment the channel is measured, the channel information is sent to the transmitter sends the information to the receiver, 10 milliseconds can pass by easily. So if the channel is varying every 1 millisecond, this feedback, this closed loop is nearly useless. So that's why you need to be very careful when you specify the network configuration. In a static environment, it does work well, but we are finding in the field that in a mobile environment, the closed loop becomes an issue. And even if we are using beamforming, the multipath can change the perception of directionality, and you may be sending the beam to a previous location but not to the actual location of the UE.
Okay, moving on to the next question. Can users have different antenna ports allocated in the same subframe?
Well, yes. Yes, because a single user, it can have DCI, a control channel allocated that will use one port. It can have also data allocated that will use another port. It may have using the same port, but it may be using a totally different set of ports, because the control channel uses QPSK and generally sent through one physical antenna, while the data can be using spatial multiplexing, be sent through 4 antennas, or using beamforming and being sent through 8 antennas. So yes, the answer is definitely yes.
Okay, we have a number of other questions that keep coming in, but in the interest of time, I'm going to take this as the last one, Len, and then you can move on. A transmission mode has more than one antenna scheme. Why?
Well, good observation. I believe I explained this, but basically, exactly, I will use the previous example of a control and data. So the control, I cannot use 8 antennas. I cannot use beamforming. So it has to be sent in QPSK, and because it's the control that will tell you or the UE what antenna system to use. So the control antenna system is predefined. It's QPSK port 0 or 0 and 1, and that's it. And that's negotiated periodically between the ENB and the UE. But for the data itself, that theoretically is much larger packets than the control packet, although that's not always the fact, then the control packet will specify what kind of antenna arrangement will be used. Is it transmit diversity? Is it spatial multiplexing, and so on? Okay. Any more questions? Or?
There are more, but Len, let's move on because we're running out of time.
Okay. Yes, it's a lot of information, and now that comes the fun part. Multiple input, multiple output, MIMO. Well, let's speak a little bit about a multiple antenna arrangement system. And I will illustrate this in this drawing here. We have the transmit signal. This transmit signal will be processed. And when I say, of course, it has all those facts and so on that we explained in the previous webinars. But it will also be, and what I call here transmit signal processing, it will be assigned to antennas. And this assignment to antennas is something complex because you may have to code, to use precoding values based on information that you receive, that the ENB or DOE received from the other side. So there is a whole process that will prepare the transmit signal and send it to multiple antennas. And that's why it's defined multiple in, is the in to the RF channel. Now, on the receive side, we can have multiple receivers. So each receiver will have an input of the receiver of the RF channel. That's why it is called multiple out. So that's why we have MIMO. Okay, and this received signal has to be processed. So I have to find a way of combining the information from multiple receivers. You know, it's like having two watches. Which one, you know, do I believe is the right one, or how do I calculate? Do I an average? Do I whatever? So you can see that we have a transmit signal processing and receive signal processing. In the middle we have the RF channel. But then, okay, we have then what we believe is the received signal. But what does this received signal tell us? So we must have another device that is the constellation detector that will say, well, this signal that you received at this moment, it belongs to this modulation and this modulation point. So we will have to analyze all those three elements, and we will have also to deduct how do we calculate the RF channel. To do this, instead of giving you all the theory at the beginning, I changed a little bit the way I'm presenting this, and I will add the different concepts as we go through the different MIMO arrangements. The first MIMO arrangement is CISO. It doesn't use the letter M, but if you make M equal to 1, that's what you get, single in, single out. And that's the most straightforward. So we have one transmit antenna and one receive antenna. Until today, basically, we would analyze this and say how much fading we would expect here by looking at the K factor that we already explained. So we look how much fading we have, and we can calculate what is the bit error rate, and we can calculate what is my required SNR. Here I basically draw the same thing, but now with a little bit of mathematics. So we are sending a signal S. This signal S will go through an RF channel, and this RF channel I am representing by the exponential function that we discussed today. And as you remember, the exponential function is a sine plus a cosine, so it's nothing of the other world. So basically, the I and Q of the constellations that are sine and cosine that I am sending, they will be distorted by the RF channel that has a sine and cosine response. And this will arrive in the receive antenna. But together with this, whatever is left of the signal, noise enters also. So now my receiver, it will have the signal times a channel response plus the noise. Very straightforward. Well, it happened that the channel response will not be flat. It will have some things like this. And those are what we consider our fadings. So each time I have a fading, small fadings, the FEC can correct. Large fadings will cause errors. Okay, and the errors that cannot be corrected by the FEC will have to be corrected through repetition. So people said, well, is there well, before this R0 signal that arrives here has to be detected in terms of constellation. And because it is distorted by noise, distorted by the RF channel, it's equalized even before it goes to the detector, because we send information, known information that we call pilot or reference signals, and those signals are used to sort of calibrate the response of the RF channel and then to adjust and equalize the received signal. Once the signal is equalized, it goes to the constellation detector that we call here maximum likelihood detector. Well, why? Because it's not absolute. The signal is distorted. It is moved in relation to the exact point. So what we will try to find is what is the most probable position in the constellation. Well, there are several methods of doing the maximum likelihood detector. We have successive interference cancellations, fair detectors, linear detectors, and then we have that are, all of them are suboptimal. Then we have the more advanced detectors like decision feedback and nearly optimal detectors like as fair detector. Of course, better the detector, more complex it is. So before we can proceed, we need to do a definition of Euclidean distance. And basically here we have a constellation, 16 QAM, and here we measure the signal. So this signal can be either this here, can be here, can be here, or can be here. If I measure my distance to each one of the constellation points, the minimum distance is our maximum likelihood. So most probably this signal belongs to this signal, to this constellation point. Well, maybe not, because maybe if it had a big error, it belonged here. So, but that's why it's the maximum likelihood detector. And this is the formula that we use, that is basically a Pythagorean formula. And there is a trend to use the squared of the Euclidean distance, so it emphasizes these differences between that are very, very close to each other. It really brings it closer to the one that is closer. So that's the minimum constellation distance, and the maximum likelihood detector then searches for the minimum constellation distance. In our case, this is relatively easy because worst case we have to do 64 calculations. So for QPSK, for a single symbol, we need to do 4 complex calculations to find the Euclidean distance. 16 QAM, 16. 64 QAM, we need to do 64 complex operations. The problem comes when now we start having two antennas, each one sending a different symbol. So now we have to look to 2 to 12. So in reality we have to do 4,000 complex operations. And if we have 4 symbols, so we are sending 4 different users at the same time, we need to do 16 million complex calculations. So as you can see, sending different information makes also the processing very, very hard to do. Next topic is SIMO or SIMO, single in, multiple out. So basically we have one transmit antenna and more than one receive antennas. And this technique has been used already for many, many years, since I would say nearly the beginning of wireless as we know it today. And there are 3 basic techniques: diversity selection combining, equal gain combining, and maximum ratio combining. So we will analyze each one of them because they are very, very important to understand the behavior of the receiver. So let's start with receive diversity. We have 2 channels now. If you look here, we have 2 channels, H0 and H1. And we have 2 received signals, R0 and R1. It's like having 2 watches. So which watch do we use? And that's where the diversity selection comes in. Diversity selection, basically, you see you have 1 channel here, 1 channel here, and then we come here to an RF switch. And basically what this RF switch does, it switches to this side or to this side. So it only gets one of the signals at a time. Either it gets this one or it gets this one. Okay, and how does it do this switching? Well, through a channel estimation here, and it says, well, yes, what I'm receiving looks good, or, well, I'm not receiving anything, switch to the other side, please. Okay, so, but there is only one constellation coming in, and this constellation then goes to a maximum likelihood detector. Well, not constellation, one value coming in from the symbol, and this value goes then to the constellation detector. In equal gain combining, there is no switching. Both signals are combined and added together, and they go to the maximum likelihood detector. Well, you will say, well, yes, because if one signal fades, you know, the probability that the other fades at the same time is very small. So I will always have a signal here. Yes, that's true, and it really helps with fading. But because the 2 paths are different, they are distorting the signal. And this signal distortion is sort of an interference. And if this interference is different from the interference suffered by the pilot, then you may have problems. So equal gain combining is not very popular, although there are people that are using. Wi-Fi uses diversity switching. But the best methods would be the maximum ratio combining. Of course, it's also the method that requires more hardware and is harder to implement. But it has the advantages, I would say, of both. The equal gain combining and the diversity selection. So here we have still one transmitter, one information being transmitted two RF channels, but before we do the sum, we do a channel estimation and we equalize the received information. So we correct the received information with the channel estimation. So basically we synchronize both the information coming from both antennas, so they can now be equally combined, but they are not distorting each other. And that's a very good way of resolving the issue, but it's not also perfect. But it has some improvements, and then the information goes to the maximum likelihood detector. Let's go now to MISO. So we are getting more and more complex. And MISO, or MISO, basically we are transmitting from two antennas and receiving on one. Is it better than SIMO? Or what is better, MISO or SIMO? Well, let's see. This is what we call transmit diversity. And to analyze transmit diversity, we will use matrices. And there are basically three types of transmit diversity, as there are three types of receive diversity. Receiver-based transmit selection, transmit redundancy, and space-time transmit diversity. Those are also, this is already MIMO, so I need to remove this. This is transmit and receive diversity, and this is a subcase of this one. So there are basically three methods. So look at this. Received-based transmit selection. Basically what we do is that we transmit on side 0 on this side or on this side, but only one side transmits at a time. This is good because I can receive, I need to receive a feedback from the receiver. If I don't receive the feedback, I say, wow, the receiver is not hearing me, so let's transmit to the other antenna and see if it improves. Or the receiver can even say, look, your signal is not very good, I'm having a lot of errors. Change antennas and see if it improves. Okay. Then we have transmit redundancy that is very similar to equal gain combining, but the combination is done in the air. So we have here the two equations. The advantage of this one in relation to the previous is very, very small. It's again fading. But again, I have the same issue of the multipath that I had in the equal gain combining. So the issues are very, very similar. I nearly solved the issue of the fading, but I am also interfering into myself. So people came to a very clever way of minimizing this interference. And what they do, they add a time component to the space diversity. So the two antennas provide me space diversity. Well, what if I also have a time diversity? So the two antennas, they don't send the same information anymore. They send different informations. And this was a very simple method. There was many people developing this, but Alamuti proposed a very simple method that we will illustrate here. So what he would say is well, look, I have two antennas, and I have two symbols in time. I will send S0 on this antenna and S1 in this antenna. Of course, they will interfere with each other. Then I send the S1 conjugate minus S1 conjugate, and I send S0 conjugate. of course they will interfere with each other. But let's write the equations. So the receiver 0 gets this signal. Remember that I'm sending S0 and S1, right? Here, S0 and S1. The next symbol, the second symbol, I am getting this. So what happens now if I add one with the other? H0, and I multiply it by the channel estimation. The two receive signals by the channel estimation. What happens is that when I multiply this by the channel estimation, this is a constant and this is noise. So, and S0, S1 disappears, so I get S0. When I do abstraction here, I got S1. So over two symbols, even if they interfere with each other at the symbol level, by adding the two symbols, it's possible then to decode S0 and S1 mathematically. Okay. Of course, there is twice the contribution of noise. That is normal. But because I have noise in symbol 1 and I have noise in symbol 2, but in receive diversity I also have twice the contribution of noise, but I can detect each one of them separately. And this is illustrated in this block diagram here. I have my two symbols in time here. I transmit those two symbols. This is my RF channel. It's very important though for this to work is that the RF channel does not change during these two symbols. So the coherence time should be much, much larger than two symbols. I would say at least 10 symbols. So ideally 1 millisecond. If I can assure that my coherence time is about 1 millisecond, now I will ask you, how do you assure this? Well, that's where CelSpectrum comes into play, because you can calculate what is the coherence time at every single point in your network. Okay, so that's something that is very, very important. Okay. And then, of course, here is the channel estimation, the combiner, and all of this goes to the maximum likelihood detector. Now, space-time block code is used by WiMAX. And in WiMAX, it's called matrix A. In LTE, they had to do something different of WiMAX to justify their own existence. So what they did space frequency block coding. It's the same thing. The only thing that here we have the space-time block coding. Basically, we use two symbols, two antennas, and two symbols. Here we have two antennas, one symbol, but two subcarriers. And what we find when we use CelSpectrum is the coherence time is very easy to get it coherent over 1 millisecond, but to get the coherence frequency over two symbols is a little bit much more harder. So I really am not sure that this was a smart move. Time is much more stable in terms of symbols than frequency in terms of subcarriers. But that's what is used in LTE, and that's what is used in WiMAX. And then we have the SFBC for 4 antennas. Is just an extension of the 2 antennas case. Well, we explain MISO, we explain SIMO. So now what we need to do, we can use both. Two antennas transmit, two antennas in the receive, and so on. And we can use the space-time or space frequency block coding. And here are the equations, and here is how we calculate this, and so on. And you can see here that I have only one variable and only one variable here. And I benefit from both, from receive and transmit diversity. But of course, the equipment needs to be prepared to do all of this. Finally, we reached MIMO. So M now is different from 1 on both sides. Although here it was already 2 and 2, 4 and 4, and so on. So basically, this MIMO is multiple inputs and multiple outputs. This MIMO can operate in open loop. So the transmitter is unaware of the channel. Or it can operate in closed loop when the receiver can recover some channel information, and then it can apply the methods below. It can inform the transmitter. So we can do linear decoders, interference cancellation, single value decomposition, and linear precoding and postcoding. And of course, the goal of MIMO is to provide what we call spatial multiplexing. So each one of the antennas sends a different information. Well, at the same time, on the same symbol. Of course, the information comes here, and it comes here and here. So what we have to do here, so let's see this receiver here, R0. Well, R0 is equal to H00 as 0, H10 as 1, plus noise. So we have two variables in one equation. On the other side, we have, on the R1, we have also two the same variables and one equation. Oh, wait, I have two variables and two equations. So I can solve the mathematical, I can find the two variables. And this is the matrix form. Of course, noise is always present. And that's where things get tricky, because if I have two equations, but one is the double of the other, I cannot find the variables because the equations are dependent or coherent. So it's very important that the equations that we get are not coherent between themselves. And that's where how we will need to look and see if MIMO will work or not. And to do this, I will have to go back to some theory. And pay attention that you will understand why MIMO sometimes works, sometimes doesn't work. And depending on the ambient, depending on the amount of noise. So basically, we will take a set of linear equations, H times S equal to R, as we had here. We had R times X, HS. So HS equal to R is the same thing. And we will call here what I call ill-conditioned linear equation. So this is one equation, and this is the second equation. So what will happen if we apply a little bit of noise? So we change the 4 to 4001 and the 8 to 7998. So we applied a little bit of noise on the received, on the signal that came from the channel. The solution to the equation that was 2 and 1 became -4 and 4. Well, what happens if we change the RF channel? We put a little bit of noise and our RF channel detection is not perfect. So we change from 1 to 1001, 2 to 2001, to 001 and 4. Well, 6.9 and -1.4, the solution. So you can see that the solutions are all over the map. We can still solve the equations, but the solutions are all over the map. So this is an ill-conditioned linear equation because the smallest amount of noise is enough to throw us completely off. Well, let's look now at a well-conditioned linear equation. So you can see very similar, 1, 2, 2, 3. This was 1, 2, 2, 4. 4, 7. And the result is the same, 2, 1. Let's do the small perturbation here in this signal. Well, I still got 2 and 1. Let's change now the channel. I still got 2 and 1. So a little bit of noise will not destroy my result. So it's very important then that we are able to predict if the equations that we get from the two antennas are coherent or not. And this is done through what we call a condition number that is used in the field of numerical analysis. And here it's a little bit lengthy calculation that uses a norm of a matrix that is defined by this equation here. And basically that's what was done, what I did here. So I took a set of equations, I calculated the norms, and I know that I didn't explain what a norm is, but it's impossible to do it in this time. But looking at this, you can understand what it does. You're looking at the equation. Then what I did is that I did a little bit of disturbance, calculated the norm, and then I did some ratios. And this ratio gave me a number, a condition number of 43.8 dB. If this number is larger than 10 dB, the set of equations is considered an illy conditioned linear equation set. And then I did for the other equation that was well behaved, and the number I got was 5.4 dB against 43. And this is a well-conditioned number. So it is interesting if you can calculate beforehand, before you install 8 antennas in your deployment, or 4 antennas, if it will make sense or not. So you should then do some measurements and measure the condition number, or at least the coherence between the antennas. Because if the antennas are coherent, there will be, most certainly, the condition number will be bad. Well, let's go and look at some MIMO considerations. How can I distinguish between two signals that arrive at the same time or added, and can I figure which one is one, which one is other? Well, yeah, sorry, this is a mistake here. I pasted the wrong thing. But let's look at here. And I have one signal, and so what I can do, I can rotate the constellation a little bit, and if my noise is really very, very, very small, I can still distinguish the two constellations. And that's what means it's another way of looking at it graphically, if the two antennas are coherent or not, because if the two give the same, exactly the same constellation, there is no way to distinguish between them. So there must be this rotation. So the MIMO configurations in reality becomes very complex, mainly when you have, suppose for two symbols, you can have thousands of combinations that you have to recover in the MLD. And that makes it very, very hard to analyze. Here is the formula for the square of the Euclidean distance. And you need to do these calculations thousands of times in the period of one symbol. And remember that one symbol is very, very short, it's 66 microseconds. Another thing that is very important to understand is that depending on the number of antennas, receive antennas, and the number of transmit antennas, we have a whole set of possibilities here of what can be activated. And this then takes us to adaptive MIMO switching, where the equipment automatically will choose between the best solution. It does this based on feedback from the receiver, on the CKI number, that is the feedback, and also on previous successes and failures. So if it's using one mode and nothing gets through, doesn't get X, so it changes to a more resilient mode. So this is called adaptive MIMO switching. But generally it is based on the SNR measured. Another way of also implementing MIMO is multi-user MIMO, and there are two types, the uplink and the straight multi-user MIMO. In the uplink, basically, what we do here is that we connect now different users. We send the information to different users, and because those users are very much apart, there is a larger probability that the signals they receive are not coherent, that they transmit, excuse me, this is only on the uplink. So the signals received by the receiver at the uplink, at the ENB, they are not coherent. Multi-user MIMO then uses beamforming to beam signals to the users from the two antennas. But the burden here is passed to the scheduler that now has to schedule users that are far apart, because if they are in the same locations, they will have get both beams. So then the scheduler becomes extremely much more complex, and sometimes there is no solution, so it has to, it cannot use spatial multiplexing because it cannot allocate enough spread users and so on. Well, all of this said, one way of calculating also the correlation between antennas gives us a very good idea of how well conditioned will be the numbers, the equations, the linear equations. And here we show the antenna correlation. So we have two transmitters, two receivers, and here are the equations to calculate this. And this correlation can be calculated with different values, different ways. Here I show the correlation of a set of numbers. So how is 1, 2, 4, 5 correlated to 1, 3, 5, 7? And then we can calculate, and this gives us a correlation coefficient of 0.98 because they are varying in the same direction, so they are highly correlated. There is the person product moment correlation coefficient, that has this formula that is used to calculate the correlation between antennas. Or we can use the variance and the covariance. We started implementing the person, but because we have complex numbers, we had to use the variance and the covariance. And with this, we were able to create the variance and covariance matrix. So CelSpectrum really analyzes the correlation and provides the correlation on a pixel by pixel basis using the variance and covariance matrix. Oops, sorry, okay. And here you can see in a drive test, okay, how the correlation varies point by point. So if you have a correlation, you know, better than 0.25, so here you may have a capacity of using spatial multiplexing. Okay, the next topic is AIS, and AIS is can mean many things. Antenna array system, advanced antenna system, adaptive antenna steering, or beamforming. That in the end means the same thing. So beamforming, I think, is one way of expressing it. Basically what happens is that if we have a set of antennas, so we have here 8 antennas, suppose, and the distance between antennas is fixed, so we have a antenna housing that assures that the antenna are properly spaced and so on and so on. We can, by changing the phase of the signal that arrives to each antenna, we can then change the angle of the antenna beam. So we can then point to where the user is. And this is generally what will be used with above 4 antennas. Is really we are using beamforming. Next, I give a lot of slides that were obtained from the literature that average several authors and so on, that gives an idea of requirement of SNR and bit error probability for different scenarios and multiple antennas. All of this has to be taken with a grain of salt because those are measurements generally done in a lab environment where, and also not all the settings are specified or are understood. So this gives us, I would say, a ballpark figure, and you need to have something much more precise from your radio vendor that applies to your conditions. In our software, we provide some default values that are more exact, of course. And these are the different for relay channel. This is for relay channels with the MRC. This is with Alamuti also. And then we have SISO and so on. So there are several curves here. And some curves, they give a gain. And that's where you need to be extremely careful. In reality, there isn't really a gain. There is a compensation of loss. So the gain can never be larger than the loss that happens due to some reason of fading or so on. So these gains, basically, they compensate fadings or other effects. So we need to be very, very careful and never take this as an absolute numbers. They work, yes, as a relative difference between the different methods. It gives them a good idea if one method is more efficient than the other, but not much more than this. Same for transmit diversity and spatial multiplexing and collaborative MIMO. Okay, let's do a break here.
Okay, Leonard, we have a number of questions, but in the interest of time, I'm going to pick up 2 because we're over our allotted time already. I just want to make a quick little announcement that if we don't get to your question, we will certainly answer it via email. as well as post it to the FAQ section on the website. We will send off a link once the recorded session of this video, this presentation has been posted, so that you can all see that as well as the slide decks and the question and the FAQ. With that said, Len, the question here, what MIMO schemes are most commonly used in Wi-Fi and LTE?
Well, Wi-Fi basically, I would say it uses the receive diversity, it switched receive diversity, so it changes the receiver, and I saw also Wi-Fi with transmit diversity. There are some very specialized Wi-Fi that use beamforming, but not everybody offers this, and there are also spatial multiplexing. You have 2x2, 3x3 solutions of Wi-Fi, but those in Wi-Fi, those gains mainly happen in stationary indoor environments. If you try to move it to outdoor, the beamforming and everything else doesn't perform as well because of the characteristics of an environment that is not static, stationary, excuse me. In LTE, of course, theoretically all of this is used, but I would say that in a mobile system, spatial multiplex, generally the Alamuti can be used, but the LTE doesn't use Alamuti, uses the space frequency block coding. That will be used, but spatial multiplexing will be used only in few selected locations that are more or less stationary. And when I say indoor, it means that the transmitter and the receiver should be in the same ambient when I was referring to Wi-Fi. In a mobile environment, spatial multiplexing will be used very, very seldom. In a stationary environment, you may have if you have point-to-point connections, no, point-to-multipoint connections, but everything stationary, fixed, then you can have, spatial multiplexing in 40, maybe 50% of the time.
Okay, let me see here. I'll grab this one here. Do we have access to CelSpectrum measured values so we can develop our own analysis algorithms?
Yes, definitely. That's the idea of CelSpectrum, is to provide the measurements. So, each operator, each university, even each engineer can extract the values he wants and can tailor the reports to its requirements. We are also very open to design new reports and so on. So we already have customers requesting new characterizations and so on. So yes, definitely.
Okay, Len, you can move on in the interest of time.
Okay, let's continue then. Let's speak about the new products. Basically, I will not speak about CelSpectrum because we already covered a lot of CelSpectrum. Let's speak a little bit about CelDesigner. That is a new generation of planning tools, and there's a collaborative work with operators that we are doing, and we are open to your input. So CelDesigner is basically a new generation of planning and optimization tools. We are very, very enthusiastic about our work here. All our engineers want to work on the projects, and everybody brings ideas and suggestions. I don't like it very much because it's delaying the project, but the product is getting fantastic. really we are improving it. And the main challenge really is to able to model, this multi-technology, multi-band, multi-everything, multi-antenna, multi-everything networks that are been available now, that the existing tools, none of the existing tools can do it. And that's what we are bringing into CelDesigner with great success. So it has simultaneous support for multi-technology. It does a full representation of the network, and more deeper we go, more cases we have, and we are even supporting things that are not yet fully available, but will be available in the next few months or year. That is, things like active antennas, where the power amplifier will be in each element of the antenna, like hoteling, where we will have only the RF head distributed, and all the intelligence will be concentrated, and so on. So all of this, it's been considered into CelDesigner. I am not going through each bullet point here, mainly because those bullet points are changing on a weekly basis as we evolve the project and we improve and we add new features and we find roadblocks and we create new things. So it's a very exciting moment for the team, and I would say for me also, because first thing I do in the morning is to see what else did we find, this evening, and what did people think at night, and so on and so on. Full Google Earth integration. We brought Google Earth into the tool, so we don't export to Google Earth. Of course, we export if we want to, but we don't need to. We have a network master plan. We integrate field measurements. We do KPI integration, fantastic database editor, antenna editor, and integrated backhaul planning, and so on. Well, we came to the end of our webinar. I would like to thank everybody. I hope you enjoyed it. I enjoyed it, so I'm really pleased. And this is the last webinar of this year, and I invite you to come to our week boot camp in UWI, or UWE, I don't know how to say it, and University of West Indies in Trinidad on December. Thank you so much, and Roy, you can close the session.
Leonard, thank you very much for an excellent presentation, as well as all the webinars you carried out this year. Thank you. Also, very special thanks to all the attendees. We are open to accepting ideas for webinar series for next year. So if you have any ideas, please send them to webinar@celplan.com. Thank you once again, and we hope to see you with us in the future. Thank you.